looked at 3 different monosaccharide examples. Right, glucose is where it's actually wrapped around, and connected to that oxygen in the ring. We can tell the difference between glucose and galactose as far as the structure is concerned by that on the left-hand side of our sketch, the hydroxyl groups are alternating. On the galactose, they're going to be both up and up positions, so they won't be alternating in that spot. As far as fructose is concerned, it's only a 5-carbon ring. The carbons, we have 1, 2, 3, 4, and 5. This carbon is out on another stem of it, so we only have a 5-sided ring there for fructose. That kind of helps you differentiate that from the other 2. Now, I mentioned before that these are hexose monomers or monosaccharides, meaning that they contain 6 carbons, but there are several others that are used to form polysaccharides. Right? These are not just there's not just 3. There are several other monosaccharides that you can come across to build larger chains of them, larger molecules. How are polymers formed? Right? And the key thing here is through dehydration synthesis. Dehydration meaning to remove water, synthesizing meaning we're building or making something. Right? So if we take our friends glucose and fructose here, they are 2 monosaccharides. We want to put them together. We will remove the hydroxyl group from one, the hydrogen off of a hydroxyl group of the other, forming water. Right? That will be taken away. And what is left is that glycosidic linkage. That's that special term for that linkage that's formed through dehydration synthesis. Right? What we'll find is to go from monomer to polymer in many of these organic molecules, you will run through dehydration synthesis to make that happen, to make that chaining event occur. And so this would be the formation of a disaccharide, sucrose, because it contains 2 connected monosaccharides. Some other disaccharides that we would consider, maybe lactose or maltose. All right, so lactose is a combination between galactose and glucose. So we form that connection through dehydration synthesis as well. The same thing with maltose glucose with other glucose molecules forming that. And these are all glycosidic bonds, right? And by definition, just so you have it sketched in someplace, it's glycosidic if it's formed by 2 monosaccharides through dehydration synthesis. That's the key. This connection, this covalent bond is made through that dehydration synthesis. And you'd be right in the thought that, well, we have hydroxyl groups hanging out here. We could probably build more to this chain. We could make we could build to an oligosaccharide or even a polysaccharide going to 10 or plus more units of monosaccharides chained together. But we just want to kind of stop short here with just the first dehydration synthesis component with these disaccharides. Right? So 2 monosaccharides together will form these disaccharides. Okay, so if we're going to go even larger, if we're going to make even larger chains of these guys, go beyond like disaccharides to oligosaccharides or polysaccharides, ranging from 3 to 10 and more monosaccharides or monomers chained together, right? That's what a polysaccharide would be, a long chain of monosaccharides. And one that we could consider would be starch from plants. All right, in starch from plants, we're going to see that we have glucose connected to another glucose, connected to another glucose, and again, through, you guessed it, dehydration synthesis. Right? I noticed I included the CH2OH flag, the little outlier, the little bit of the molecule that kind of sits out and away from the ring, because when starches are formed, they're going to chain themselves together in this way where they're all facing the same direction. They're all kind of lined up in the same way when they chain from one to the next, right? And so these would be when plants have an abundance of a simple monosaccharide. That's what they're going to store it as. They're going to store it as a starch molecule for later use later on. And then, well, of course, we cook the plants and eat them and take advantage of the fact that they have starches in them for us to harvest the glucose from them, or amylose, or whatever simple sugar might be there. right? We also, if we have an overabundance of glucose, will store it, right? And we'll first store it in a temporary, like emergency energy molecule known as glycogen, right? And this is done in your liver and your muscle tissues. And the difference between the starch that we find in plants and this, I suppose you could consider glycogen to be an animal-like starch, is that it's formed by branching glucose molecules off of a chain, right? Instead of them all being oriented in the same direction, where we see chaining events happen, we can see that some glucose molecules will actually be flipped, and then we'll see branches, long branches of these glucose monosaccharides connected end to end to end to end. But this is, again, used for emergency storage. So if we run low on glucose, then our next step, I suppose, to find some energy-rich molecules is to start working at breaking back down this glycogen. All right, then another polysaccharide for us to consider that's built from simple carbohydrates or simple sugars or monosaccharides would be cellulose. All right, so when we look at simple sugars, they are like very quick energy loaded molecules for us to take advantage of. If we can then build them into larger chains of them, polysaccharides or polymers of carbohydrates for short-term storage. Right? We can also use them, we don't necessarily use them for this, but plants will also use them for structural components. Right? So cellulose is made by plants and it's used by plants to make their cell walls. And it's different from their starches in that every glucose is flipped. Like every other one is flipped opposite to the next. Now, this works rather well because if you consider like one of these strands, like not just one of these strands will make the cell wall. It's going to take bundles of fibers of these guys to make the cellular walls. But if you were to put another one of these chains near this one, it's very easy to see where these hydroxyl groups are hanging out, that we might see hydrogen bonding happen from one chain to the next. And that's going to make them very, very strong and provide a structural support component to this growing, fiber that we would put together. And then bundles of these fibers are put together to form the cell wall. So carbohydrate polymers have two main purposes: short-term storage of energy, and then also structural support in plants. We see it very evident, like in when you bite into that crisp stalk of celery, or that crisp salad or whatever. All right, some more information then when it comes to starches, glycogen, as well as our cellulose. Right? The starches are going to be like hundreds of monomers long. Right? So that's what makes it a polysaccharide. It can be glucose. It can be any simple monosaccharides chained together in the same direction. Amylose is another simple sugar that is found like in potatoes and stuff. So like potato starch has amylose like chained together. We would use an enzyme when we eat the potato. We would use an enzyme known as amylase, with an ASE on the end. If you see that next to like the root stem of some sort of like monosaccharide name, that's usually an indication that that's an enzyme that will work specifically on that type of sugar. Right? So we would use amylase to break down these amylose starch molecules, to use them for our purposes, to get the simple sugar out so we can use it. This is actually easily done digested by humans, right? So we can break this back down eventually into glucose or amylose molecules and then use them. And if we have too much to use at one time, we'll short-term store it into glycogen, right? And so glycogen is that branched chain of, or forked chains, I suppose, of glucose or amylose or simple sugar molecules. And again, used for short-term storage, and it's usually for quick energy reserves. So for those of you that are in athletics, when you go to do a longer duration event, your body will first use up the glucose that you have freely available in your bloodstream and already ready in your cells. But when those run in short supply, then it's going to start burning your glycogen reserves. to help facilitate cell respiration and keep you moving. And then finally, a thing on cellulose. Humans can't digest this. Right? We don't have the enzymes. We lack the enzymes necessary to break this guy apart because it's very, very, very robustly put together with the alternating flip of these monosaccharides that build it. So cows could work on this. Termites have bacteria in them as well and that allow them to biochemically break this molecule back apart. If you watched, I think the notes on Bozeman mentioned the fact that like if you were to try to eat like a chunk of wood, it would be passed back out as a chunk of wood. Right? You're not going to be able to break that piece down. Now that's okay though. When we chomp on plants, we eat that salad, we crunch on that celery. That stuff we can't break down. We usually rename it as fiber. It's bulk that helps move things through our digestive tract. So it's a lot easier for your digestive system to be able to work things and move things through in an efficient way if you do get a supply of fiber in your diet as well, because it gives your body something to push through and help move things through your system versus just trying to, I guess if you consider like a tube of toothpaste that's open a little bit. If you try to squeeze things through a certain direction, if it's all like liquidy and there's not a whole lot to push against, sometimes it gets some backflow the other direction. Not everything flows out as it should. So fiber can be helpful in your diet to help things flow the right way. And then chitin is actually like cellulose. It is a polysaccharide, but it has, I think it's laid out like a starch almost, but it has an extra nitrogen group attached to it, and that makes it have the property like being like leather in its pure form, and so that builds the exoskeletons of insects and even like small like arthropods as well, like crabs and lobster. But also in surgeries, we will use sutures that are made of chitin material, and because they'll eventually dissolve after the wound has kind of healed itself or patched itself back up naturally. So those dissolving sutures are using a polysaccharide really to make that work. So kind of cool. There's a couple oddball pieces of information. Just remember that simple sugars are 1 or 2 saccharide units, so mono or disaccharides. Complex sugars, just to kind of review and summarize, are 3+ saccharides or more, so your oligosaccharides or your polysaccharides. And really, what's really cool about carbohydrates is that we get about 4 calories of energy per gram of them. So they're loaded with a good amount of energy in them for every gram that's present. And we simply break the bonds. If we break those bonds in those glucose molecules, that's going to release that energy out, and we can use that then for respiration or whatever. So how do we break these polymers back down? Well, the process will be hydrolysis. Right? Hydro meaning water. Lysis or lyse meaning to cut or break. So we have our disaccharide friend sucrose, right? And connected by this glycosidic linkage, this covalent bond using an oxygen molecule in between, or oxygen atom in between. And in order to break this down, of course, we're going to need water, and usually an enzyme is in place to help lower the energy needed to make this process work. And if we're trying to break down sucrose, then we're going to use the enzyme sucrase to break it down. Right, so you can see again where the root of the polymer or of the sugar is going to be used with ACE on the end to represent the enzyme that will be doing this. And so with a little bit of water, we can reattach a hydroxyl group, plop the H back onto this oxygen to make it a hydroxyl group again, and now we're back to having our glucose and fructose. And so let's move into lipids today. Lipids. The guy we have on the screen is a triglyceride. We know that the tri comes from the fact that it has 3 fatty acids attached to it. But we'll talk a little bit more about the construction of these triglycerides in just a moment. But lipids in general, right? If you wanted to figure out like how do we classify or how do we differentiate between carbohydrates to a lipid, it's going to be that these are hydrophobic molecules. right? There's a lot of them. So it's a diverse group of hydrophobic molecules. Some are more hydrophobic than others, but they all will have a water-fearing or water-repelling side to them. So they are diverse hydrophobic molecules. All right, so we're going to bounce back and forth between this and some sketches. So I guess try to be patient, I suppose, here. I did a little bit of a revision here with the lipid structure. We could really classify lipids into three main categories, right? They can be phospholipids, which we'll look at those first. They can be fats, which we'll look at those obviously second, or they could be a steroid, right? So these are three major categories of lipids. Underneath fats, you can put like your greases and oils and stuff like that, right? But really, we have three main sections or divisions when it comes to lipids. Right? The monomer, the thing that's going to be like the building block of these lipids, will be fatty acids. Right? That's going to be our monomer to work with. If we connect some of them together, we can form them into different lipids. These phospholipids, fats, and steroids, the larger molecules. Okay, so before we look at what a phospholipid is constructed from, let me switch back out here, and we'll do a little drawing for a second. Because first we need to understand like what a fatty acid is, right? Like what makes it fatty and what makes it an acid, right? Well, what makes it fatty is it eats too much. No, I'm joking. That's not true. These are molecules; they don't eat on their own. But what makes it fatty is that it's water-fearing. It has a water-fearing component. It's hydrophobic at some end of it, right? So a fatty acid is going to have a hydrocarbon chain, right? So we're going to have carbon to carbon to carbon to carbon to carbon. And we could represent this with just a zigzag line, each vertice, each end of a line being a carbon atom. But for now, we'll just kind of do this. And we recognize that there should be like hydrogen kind of sketched in with these guys. So we'll sketch in hydrogen. And again, normally we don't write all these in because it just takes a lot of time. And this can like go on to like, could be like very, very, a good number of carbon atoms that are strung together, usually between 16 to 18 carbons, yeah.
Why isn't there one on the official?
Because I haven't got there yet.
Oh.
Yep. All right, so this would be our hydrocarbon end, right? And this part of it would be hydrophobic. Right, so that's where it gets the fatty from. Okay? That's where it gets the fat to its name. Right? The other part of it is a carboxyl group is on the front end of this. Carboxyl is COOH. It usually has a negative charge on it, and this is carboxyl. Right? And this is going to be right here where we have a single bond down to an OH group and then a double bond to oxygen, COOH. Right, so this is carboxyl is this guy right here. Right, this is what makes it an acid. Right, this carboxyl group. So it's fatty because it has the hydrocarbon chain, which is water-fearing, and it's an acid because it has this carboxyl group. Well, you might be thinking, well, okay, I'm going to go ahead and get rid of this because I have some room to draw. You might be thinking, all right, well, if this makes it acidic, then how? Like what happens here? Well, we should recognize or remember that what gives something or what gives a solution a low pH. What about it would make it have a low pH? What would we see in higher abundance in a solution that's acidic? Yeah. Hydrogen ions. Yeah. H+ guys. Yep. Absolutely correct. So when this guy actually goes to hook up with stuff, because this is our monomer, right? This is going to be connected to something, right? It's going to lose this, right? And if that goes out by itself alone, it's going to be H+ by itself, right? So it's a very, very weak acid. These fatty acids are very, very weak. But if this guy is going to give up a hydrogen, we probably have something else that's going to donate a hydroxyl group and ultimately form, which is water. Right? Right? Remember to connect things, to connect monomers to other things, we're going to use dehydration synthesis to do that. So this is going to give up the H part of the H2O. We need the OH from something. All right, so now, like, what is that something? All right, so the phospholipid, right? We have the fatty acid under control. We sketched it out. Now we're going to look at how we build a phospholipid. It has three parts to it. The head of it, or the water-loving end of it, is made of glycerol and phosphate. Right, we're going to look at those in just a second. The third portion or part of it is going to be the two fatty acids. So it has a head made of glycerol and phosphate, and it has two fatty acids attached to it. Its function is to make up the cell membranes. So this is rather important, because if we're constructed of trillions and trillions of cells, we don't want our cells oozing all over the place. Right? We need to keep all of our liquids to ourselves. So we need something that's going to hold liquids in and keep other liquids out. Like we don't want to jump into the ocean and dissolve. That'd be bad. Right? So we need something that these phospholipids are going to do just that. Okay, so we'll hop back out of this and let's construct ourselves a phospholipid. All right, so we're going to make ourselves a phospholipid, no problem. First thing is, we need to start with glycerol. This is glycerol. Right? It's 3 carbons in a chain, and then it has 3 hydroxyl groups on it. So that OH, OH, OH. Right? We're gonna draw it this way because it'll be easier to kind of sketch up what happens as we move along. But so we have, this glycerol. It's called glycerol because, or has OL in the name. It has this OL in the name because it's an alcohol. Alcohols are carbon chains that have hydroxyl groups in them. Right? The OH makes it an alcohol. Right? So glycerol means it's a 3 carbon chain here with 3 hydroxide groups on it. All right, so that kind of takes care of that. All right, so let's take care. We know it's going to have 2 fatty acids on it. So we might as well go ahead and get that taken care of. So our fatty acid would be, we're going to have a carbon, and then we have, let's see, an OH group here, and then we have a double bonded oxygen, and then we have this hydrocarbon tail. Right? There's our fatty acid. I just didn't draw the carbons in. Right? We can just use it. We can use structures to show this. Right? We need 2 of those. Okay, no problem. So another carbon, a double bonded to oxygen, a single bond to OH, that's our carboxyl group, and then we have our hydrocarbon chain. Okay, so we have 2 fatty acids. Dehydration synthesis would take this guy and this guy, these 2, these guys will combine, and they will form 2 waters. Right, so that's gonna put these guys together. So there'll be a covalent bond between this oxygen will be gone. So this covalent bond will connect to this oxygen here, and this guy will connect to this oxygen here. Right, so now we have 2 of our fatty acids attached to our glycerol. The only thing left is phosphate. Phosphate is going to attach on this guy. So this guy will kind of get moved onto the phosphate, and we'll have phosphate is PO4 with a 3 negative charge. That's what phosphate is. It's going to connect itself here at this position on our glycerol. All right, so we have our 2 fatty acids, our glycerol, and our phosphate, and this is going to be our phospholipid. There is room for other things to attach to the phosphate, right? So connected to this guy, I'm just going to put a purple blank mystery box. Right, so here's our mystery box. This mystery box could include some other fantastic molecule that gives it a special name. Right? This will be a something phospholipid. right? And whatever that something is whatever this R group is that we attach. We call them R groups because it could be like the something, some other organic molecule that we get. The glycerol with the phosphate is going to be water-loving. So it'll be a water-fearing, water-loving. And the reason that that's important when it comes to cell stuff is, say we draw like a very simplified version of this. Here is our head with our glycerol and phosphate, and here are our two fatty acids, right? Right. So if we line these guys up like this, right? Our cell membranes are phospholipid bilayers, bi meaning two. So we're going to have two layers of phospholipids to make our cell membrane. So that means that on the other side we have other phospholipids, and their water-loving end will not want to be near the water-hating end of the other ones. So they're going to line up like tail to tail. These are supposed to be hydrocarbon chains, just believe. Just believe. All right? And so this then would be your cell membrane. This would be like the good stuff in the cell you want to keep, cell liquidy things. And then out here would be everything else that you don't want necessarily in the cell. Right? So this is your phospholipid bilayer, and this one unit is your phospholipid. Right? That's why they're important. And that's why we need them for cell membranes. All right, so triglycerides. This is actually easy. The hard part's over because we figured out like what glycerol looks like. We attached some fatty acids. We looked at what those look like, and we also considered phosphate being in there with the phospholipid. Right. So a triglyceride is simply going to be made of two major parts. The head of it is going to be glycerol. So we've already looked at that. It's a 3-carbon chain molecule with 3 hydroxyl groups. The tails, the 3 fatty acids, right? So in the phospholipid, we only had 2 fatty acids. Well, instead of having a phosphorus or phosphate group on this, every single hydroxyl group gets partnered with or dehydration synthesized with a fatty acid. So you'll have 3 fatty acid tails instead of just 2. Right? The function is to provide energy for cells, also to insulate. So triglycerides are fats. You can have saturated fats and unsaturated fats. We'll consider the differences in just a moment. But your triglyceride guy is easy, right? We talked about the features of a fatty acid. We've already done the carboxyl group with the hydrocarbon chain, the water-loving, the water-hating, or the water-phobic end of this guy. We've put them into a phospholipid, right? So here's our glycerol, our phosphate, and some special R group, and then our hydrophobic tails, our fatty acids. They can be represented by like the circle being the head, and then 2 fatty acid tails, right? We've looked at that, right? Glycerol molecule with 3 fatty acids. This is a triglyceride, right? So each of the hydroxyl groups through dehydration synthesis has been linked up with those fatty acids. Now, in terms of like what fatty acids you have there, they can all 3 be the same, or you could have different fatty acids at each position. And it really depends on where you're sourcing the triglyceride from, like what mechanisms are building them as to what is going to be found on them. Right? Usually animal fats are going to be saturated fats, whereas plant triglycerides are going to be unsaturated. All right, so the difference then, a saturated fat is going to be where every single position is single bonded, and you have hydrogens at every open space around the carbons. Right? It'll form a straight chain. Straight chain fatty acids are saturated. Right? So each carbon is saturated with hydrogen atoms. It's common in animal plants. Right? It's common in animal fats. And also, it's going to be solid at room 10. An unsaturated fatty acid is bent. because it has a double bond in it someplace. Could be one or several. Right? It's the double bonds that make them crooked. We got one more. Here we go. All right, so we have this double bond here between the two carbons. That's going to bend this down in a way because we have two hydrogens up here on the other side. But because we do not have hydrogens at every spot, because we have a double bond here, that makes it unsaturated. They are usually liquid at room temp, usually. So think oils, like your olive oil or sunflower oil or canola oil would all be those containing unsaturated fats. So if we have a normal blood vein, right, our red blood cells should move through that guy, without a whole lot of problem. Nothing blocking it up, nothing slowing anything down. Right? If we have too many saturated fats, though, as we consume more of those saturated fats, they're going to eventually find a spot where they kind of settle out, or they maybe find like a spot where the flow is not as quick, and so they start to glob up and form a plaquey surface on the inside of our veins and arteries. And so normally red blood cells could just flow right through, no problem, but now they're going to have to hit this little barrier and go up and around, or they could get stuck right there, and they start building up like a clot in a vein or artery. And over time, that's going to start that closed up vein or artery does not let blood flow like it should. So you're going to have reduced circulation, which is going to compound this problem, because if they cannot flow through very quickly, there are going to be more of them that pile up. And then that can result in blood clots and obviously high blood pressure, because you're trying to push the same volume of blood through a much smaller opening. Right? It's like when you turn the hose on, you don't have like a little sprayer hose on it, so you put your thumb over it. You can feel that the pressure in the hose kind of goes up a little bit behind that where you're kind of clamping the hose off. That's the same thing that's going on here. You got that clot building up, narrowing the opening that blood can move through, and it builds pressure on the backside of it, which makes everything work harder all the way around. So it's good. I mean, you want to have a good balance to your diet when it comes to cholesterol and saturated fats. All right, the last thing to mention here are steroids. Steroids are a classification of lipid in which they have 4 carbon rings that are fused together. And so I included a little diagram of a steroid. This is cholesterol. And cholesterol has, I always say that this is the house, and then it has 3 playgrounds. Like the house is just that little 5-sided ring, and then you have some 6-sided hexagons. There's 3 of them, 3 playgrounds attached. What makes one steroid different from another, or what makes this cholesterol, is the chain that goes on at the top, the smoke that comes out of the chimney of the house. Right? You don't necessarily need to memorize or commit to memory the structure of it. What you need to know is that steroids are in some ways hydrophobic, so that's what makes them a lipid, and that cholesterol is a type of steroid that is a common component of cell membranes. And we also synthesize other steroids from it. Right? So some hormones as well as some other steroids are synthesized from cholesterol. So it is necessary to have some cholesterol in your diet, but you don't want to have too much. It's like everything in moderation.